Welcome to Deep Dive, the podcast where we explore the depths of science, technology, and the boundless wonders of the universe. I'm your host, Amy. Today, we're embarking on an extraordinary journey, a journey that humanity has dreamed of for generations: interstellar travel. Reaching the stars has long been a staple of science fiction, but what would it actually take to make it a reality? How can we overcome the immense distances, the challenges of near light-speed travel, and the dangers lurking in the void of space? Buckle up as we dive deep into the physics, the engineering, and the human element of venturing beyond our solar system. Let's start with the sheer scale of the challenge. The closest star to us, Proxima Centauri, is about 4.24 light-years away. To put that into perspective, that's nearly 40 trillion kilometers. Using current technology, like the speeds achieved by NASA's Parker Solar Probe, which clocks in at around 700,000 kilometers per hour, it would take us over 6,400 years to get there. Clearly, we need to go faster. A lot faster. So, how do we achieve the speeds necessary for interstellar travel? One intriguing idea combines nuclear fusion propulsion with gravitational assists from massive cosmic events. Imagine a spacecraft equipped with a nuclear fusion engine. Fusion, the process that powers our sun, releases tremendous amounts of energy. A controlled fusion reaction could provide a powerful initial thrust, propelling the spacecraft to high speeds without the need for an impractical amount of fuel. But we don't stop there. The universe is full of gravitational wells, massive objects like stars, neutron stars, and even black holes. By carefully plotting a course that takes advantage of these, our spacecraft can perform gravitational slingshots, gaining additional speed without expending fuel. In some theoretical scenarios, a spacecraft could even harness the energy from supernovae or the spin of binary neutron stars, although the technical and safety challenges of such maneuvers are, admittedly, astronomical. In the vacuum of space, Newton's first law reigns supreme: an object in motion stays in motion unless acted upon by an external force. This means that once our spacecraft achieves a certain speed, it doesn't need continuous propulsion to maintain it. But here's the exciting part: we can apply multiple accelerations over time. Each time the fusion engine fires or a gravitational assist is performed, the spacecraft gains additional speed. These accelerations are cumulative, allowing us to inch closer to a significant percentage of the speed of light. However, as we approach these extreme speeds, we encounter new challenges, like increased kinetic energy of impacting particles and time dilation effects predicted by Einstein's theory of relativity. Speed isn't our only hurdle. At velocities approaching a significant fraction of light speed, even tiny particles become deadly projectiles. A grain of sand hitting the spacecraft could have the impact of a bomb due to the enormous kinetic energy. To protect our intrepid travelers, we need advanced shielding solutions. One concept involves using electromagnetic fields to create an invisible shield around the spacecraft. Here's how it works. 1. Ionization of incoming debris. The spacecraft emits lasers or other forms of energy to ionize neutral particles in its path, giving them an electric charge. 2. Magnetic deflection. Surrounding the spacecraft is a powerful magnetic field. Charged particles interact with this field and are deflected away from the vessel, much like how Earth's magnetosphere protects us from solar wind. 3. Energy requirements. While this method is elegant, it requires a significant amount of energy. However, if we're already harnessing nuclear fusion for propulsion, we might tap into that same energy source for shielding. Accelerating to near light speeds is one thing, slowing down is another challenge entirely. Without friction in space, a spacecraft won't slow down on its own. Overshooting the destination is a real risk. Possible solutions include: 1. Reverse propulsion, turning the spacecraft around and using propulsion to decelerate. This requires planning and additional fuel. 2. Gravitational braking. Just as we can use gravity to speed up, we can also use it to slow down by approaching a massive object in such a way that its gravity pulls against our direction of travel. Both methods require precise calculations and add complexity to the mission design. Even with all these advancements, trips to even the nearest stars would take decades at best. At 10% the speed of light, a journey to Proxima Centauri would take over 40 years. This brings us to the human element. How do we sustain life for such long durations in the harsh environment of space? Here are a few challenges that our space travelers will be facing. 1. Cryogenic sleep, a staple of science fiction, but currently beyond our technological capabilities. We haven't yet found a way to safely induce and maintain suspended animation in humans. 2. Generational ships, spacecraft designed to support multiple generations of inhabitants. This turns the voyage into a moving colony, complete with all the social and psychological complexities of a small society. 3. Psychological challenges, isolation, confinement, and the knowledge that the original crew won't see the destination could impact mental health. Robust support systems and perhaps even virtual reality environments might be necessary to maintain well-being. The hardships of interstellar travel are immense: radiation exposure, micrometeoroids, life support sustainability, and the physical effects of long-term weightlessness are all significant concerns. Moreover, there's the issue of communication delays. At interstellar distances, messages to and from Earth would take years. This necessitates a high degree of autonomy for the spacecraft and its crew. Given all these challenges, one might wonder, why pursue interstellar travel at all? Exploring new worlds could answer fundamental questions about the universe and the potential for life beyond Earth. Establishing human presence on other planets could safeguard our species against existential threats. The pursuit itself drives innovation, leading to breakthroughs that can benefit life on Earth. So, what's next? To turn these ideas into reality, we need to achieve a few things. We need advancements in nuclear fusion. This helps us to have sustainable and controlled fusion reactions for propulsion and energy. We need materials science breakthroughs. With this we can develop materials that can withstand extreme temperatures, radiation, and impacts. We need advanced autonomous systems. With AI and robotics, we can travel in space without too much of complexity as we allow the AI and robotics manage complex operations and repairs far from home. We also need the international collaboration. Achieving interstellar space exploration is not something to sneeze at, and so this requires the combined efforts of the global community. The dream of interstellar travel pushes us to rethink what's possible. It challenges our ingenuity and our willingness to take risks. While we're not there yet, each theoretical solution and technological advancement brings us a step closer. Perhaps the most significant hurdle isn't the physics or the engineering, but the human spirit. Are we ready to commit to journeys that span generations? Can we unite globally to tackle challenges that no single nation can overcome alone? Only time will tell. Thank you for joining me on this deep dive into the future of space travel. If you enjoyed this episode, please subscribe to the channel and share this video with others who have their eyes set on the stars. Also, don't forget to like the video because this will help the video gets more popular. Until next time, keep dreaming big and reaching for the cosmos. I'm Amy, and this has been Deep Dive.